All right. So I asked you guys to look at these problems as our warm-up. However, that really is our lesson today, is a review of exponent laws. So if you got to one and you were hesitant or not remembering how to do that type of problem, we're going to go back and review these. But these are very basic exponent law problems. Let's go back and look at our exponent laws real quick. And this is, again, leading into things that we're going to need to remember heading into Chapter 2. And we're going to need to remember how to work with exponents, what those functions look like, how we simplify them, etc. So let's see what we remember. Anything raised to the 0? 1, you got it. Okay. The next one is a reminder that we do not leave negative exponents. They're not happy where they are. Move them to the other part of the fraction. If it doesn't look like a fraction, we can always make something look like a fraction by putting it over 1. So I would slide that down to the bottom and make it 1 over a to the positive n. If it were negative in the bottom of my fraction, I would move it to the top. Wherever it's at, we move it to the other part. Remember that if they have the same base, I am going to add their exponents. That would be like an a to the m plus n. On the next one, when it is division, but they have the same base, we would subtract their exponents. When you are looking at this one, I always think subtract big number minus small number, but the big number wins. Wherever the big number came from is where your answer goes. So if the big number came from the denominator, my answer goes in the denominator. Big number came from the numerator, answer goes in the numerator. Okay, so big number wins. If we have an exponent raised to another exponent, that is multiplication, a to the m times n. Now this one is key, no plus or minus. Okay, if there is no plus or minus in there, you can basically distribute, and I use that term loosely because it's not technically distributing, but give everything that n exponent. A to the n, b to the n. Doesn't work if we put a plus or minus in there, right? Then we have to go to foiling. Same thing on the last one again. With no plus or minus in there, we can just give the n exponent to everything. A to the n, b to the n. What we're going to spend most of the rest of today looking at is putting multiples of those rules together, and how do we attack problems that require multiples of those rules to completely simplify. Questions so far? Okay. Then let's run through those first questions and just make sure that we are good to go. There's one for sure that we need to look at that is a super common mistake that people will make. The first one, same base, we should add their exponents, would be x to the 13th. Second one, same concept, but when we end up with an answer of like y to the negative 6th, we need to move that so that it has a positive exponent. So that's correct, but not done. So if you stopped at y to the negative 6, you're on the right track. Move that to the bottom of the fraction. 1 over y to the 6th is where we would get to on that one. Next one, division. We should subtract. Bigger number comes from our numerator, so our answer goes in the numerator. 10 minus 4 is 6. The next one is the one that people make the most mistakes on. They say either the answer is 1 or 3. What is the answer? 3. Do you see why they might say 1? Super common mistake. Okay, is that they're thinking the whole thing is being raised to the 3, or to the 0. But this is a great concept for us to look at because every single thing has its own exponent. The 3 has its own exponent of a 1. The x has its own exponent of 0, which would be 3 times 1, or 3. If this whole thing were to turn out to be 1, it would have had to be grouped in parentheses. So like 3x raised to the 0, that would equal 1, right? Moving up to the next one, exponent raised to an exponent would be x to the 15th. This one is just a good talking point for us. If we have numbers raised to an exponent, simplify it to what it actually is. So yes, it is 2 to the 4th, x to the 4th, but if we have a 2 raised to an exponent, we actually figure out what that is, which would be 16, x to the 4th. Same thing on the next one, each gets squared. And when it is a number, we go ahead and square it, x squared over 25. And in the last one, kind of a two-step process on this one, move it to the bottom so that becomes positive. And then go ahead and figure out what 4 to the 3rd is, which is 64. Any questions on that? It would not. The negative is just telling us to move it to the bottom of the fraction. And that's a great question, and one that I have seen show up a lot of answers on the worksheet today is that people are raising like 3 to the -2 and calling it -9. It's not, it's 1 over 9. The negative in our exponent just moves it to the different part of the fraction. Okay. All right, we're going to just spend the rest of the time looking at a little bit more complex, kind of one of each type here. So a multiplication with a whole bunch of complex. On a problem like this, 4a to the 5th, b squared, 2a to the 4th, b raised to the 3rd. If you have exponents outside of the parentheses, that's where you start. Okay, before we start putting the two parentheses together, we have to deal with any exponents on the outside. So that would be this 3, and that means that each of these terms gets raised to the 3rd. And if it already has an exponent, remember we will multiply. So 2 to the 3rd, we again need to simplify that down. 2 to the 3rd is 8. A to the 12th, b to the 3rd. First one hasn't changed. It didn't have an exponent outside, so it'll stay what it was. And then we are not done. If we have more than one of the same letter in our problem, we're not done simplifying. Okay, so I have 2 A's, I have 2 B's. The numbers I can actually deal with as well. Don't forget how to just multiply numbers together. 4 times 8 is what that means, right? 32. Don't overthink that. A to the 5th, b to the 12th. Same base, we add the exponents. A to the 17th. B squared, b to the 3rd. Add exponents, b to the 5th. Same idea, even if they're fractions. So again, as we see this next type, if you have exponents on the outside of the fraction, start there, outside of the parentheses. Start there, and then put the two parentheses together. But we can't put them together until we've gotten dealt with the exponents on the outside. So I would, on this first one, go ahead and distribute that 3 exponent to everything. Here, distribute that 4 exponent to everything. Okay. It is multiplication, and so we really can look at this. I know it is one fraction times the other. Well, that's multiply straight across the top, straight across the bottom, which is kind of like just having one big fraction, right? And then combine your terms that have the same base. So I've got an x to the 3rd, x to the 4th, both in my numerator. Add their exponents, x to the 7th. The y's, I've got one on the top and one on the bottom, which means subtract their exponent, bigger exponent wins. So the 8 is where our answer goes. Y to the 8th minus y to the 3rd, y to the 5th. There is only one z, nothing will change about it. It stays where it is. Questions on that? Okay. I'm going to change this next example, just one little thing. Let's go ahead and add a, let's go a -2 exponent to that z. Very important little thing that's going to happen here. First of all, I would attack it just like I did. Deal with that exponent on the outside by just distributing that all the way through to every number, and then deal with negative exponents after we have done that. So I'm going to multiply each of these by a -4, which would give me an x to the -8, y to the -12, and z to the +8. Good so far? When you go to move positive, or not positive, but negative exponents to make them positive, each number and each letter we look at individually. It's not that they all move. They each are an individual decision. So the x has a negative exponent. It moves to the bottom of our fraction. The y has a negative exponent. It will move to the top of our fraction. The z is positive where it's at. It's happy where it's at. Leave it there. So it would stay in the bottom of the fraction, z to the 8th. So every number and every letter has its own exponent. Move them individually. When you are going to combine, so that next one, number 4, when you are going to combine 2 letters, I will tell you that it's not a rule, but people are way more successful if we move to get all positive exponents before trying to put things together. Trying to remember addition and or subtraction with negatives included is where mistakes happen. So I would rewrite that first one, dealing with the y to the -6 and the x to the -3rd first, before ever trying to combine things that have the same base. Okay? So in doing that, again, assess each one individually. 10 has a -1 exponent. It's positive where it is. Leave it alone. X to the 1st, y to the 6th is going to move to the bottom of our fraction and become a +6. The 2 has a positive 1 exponent. It stays where it's at. The x has a negative exponent. We're going to move it to the top. Y to the 8th, positive exponent, leave it where it is. Now we make way less mistakes putting things together because we're not dealing with like subtraction and negatives and all of that. So now I can put them together. Addition gives me a x to the 4th and a y to the 14th. And then the number part of it is just the number part of it. And 10 over 2 simplifies the same way we would have simplified 10 over 2 last year or 5 years ago when we dealt with fractions, right? We look for what they have in common. Both divisible by 2, I would simplify that into 5 over 1 or 5. Any questions on anything? Exponent rules, fractions, negatives, anything? Okay. If our exponents turn into fractions, we still use the same rules. We just have to remember how to add or multiply fractions together or subtract fractions, okay? So for example, on this one, x to the 1/4, x to the 5/4, same base, add the exponents. So it's an x to the 1/4 plus 5/4. Well, the rule in adding fractions is they have a common denominator. I have a common denominator on this one, so I don't have to fix that. Sometimes I would have to, but I don't have to. So I just add the numerators, keep that common denominator. 1 plus 5 is 6, and that would simplify down to x to the 3/2. Any questions on that?
You can have bonus fractions.
You are allowed to have, yes, improper fraction. When you are dealing with that and a number, it might help you to remember that something like, let's say, if we had ended up maybe at the end of our problem having like 16 to the 1/2, you can simplify that. Remember what 1/2 means, right? That is the same thing as a square root. So when you see something like that, we really can simplify that. Think of what it is in terms of a radical. This is the root of your radical, so that would be a square root. These two things would be equal to each other, and it's a lot easier usually to think through it like that than it is like that, okay? All right. Speaking of simplifying radicals, that's kind of the last thing we're going to talk to you about doing today. Simplifying radicals is similar to factoring in. It depends on what math teacher you had over the years. They kind of all have their own little method of how to teach this. So use whatever method works best for you. One of the methods you can do is think of division. If I take you back to like elementary school when we learned how to do division, we kind of drew this little thing over here, right? And what I want to think about dividing is the exponent divided by the root of my radical. Okay, well, if I were to take 17 divided by 3 back in elementary school, I would say, okay, how many times does 3 go into 17? 5 times. So 5 times 3 is 15. We would subtract, and we get a remainder. Oh, you remember when math was that easy, right? I mean, those nice, pretty little division things with a remainder off to the side. Well, guys, that's kind of what you're thinking through in your head when you're simplifying your radicals. But this becomes the exponent that moves to the outside of the radical. And this is the exponent that's going to stay on the inside of the radical. Okay, so as I think about how many times does it go into 17, that's what gets to come out of the radical. And whatever's left over when I do that is what stays inside the radical. So 3 goes into 17 5 times. So an x to the 5th gets to come out of that cube root. There is a remainder of 2, which means 2 of those x's, or an x squared, has to stay inside of the cube root. So that is a method for how to simplify a radical. Not the only method, but it's one way. Okay? So try that method, or try whatever method you remember how to use, and simplify this cube root. Cube root of x to the 4th, y to the 7th, z to the 12th. So if we go through the divide the exponent, what's my remainder method? I'm dividing things by 3, so 3 goes into 4 one time. So an x to the first comes out of that cube root. There would be a remainder of 1. One of the x's would stay inside. 3 goes into 7 2 times with a remainder of 1. 3 goes into 12 4 times with no remainder, so no z's left inside of my radical. With that being said, you can have all letters left inside, you can have nothing left inside. If it all goes in evenly, you don't even have a radical left at the end. That's okay. Okay? So the last thing I want to do is just mixed numbers and variables and simplifying a radical. So take a second and look through this. Simplify your numbers just like you always would. So if I took the variables out of there, it would not change how we simplified the numbers like we did yesterday. We don't spend a lot of time with cube roots in here. I don't spend a lot of time talking to you about perfect cubes in here, but hopefully we recognize some of the smaller ones like 125. What is the cube root of 125? 5. Yeah. So this one actually turns out really nice. 3 goes into 6 2 times. 3 goes into 3 1 time. That one is a perfect cube. We get 5x squared y. On the next one, again, I think of the 54 just like I would have earlier. What was the biggest perfect square that you found that went into 54?
9.
Thank you. Okay. Square root of 9 is 3. And then we think about the fact that it is a square root. So my root is 2. 2 goes into 9 4 times with a remainder of 1. Questions on that? Okay. You guys have a worksheet for your assignment today.